In this presentation, I'll be explaining the op-amp circuits, differentiators and integrators. How op-amp can be used to implement differentiation as well as integration. Coming to the basic differentiator circuit, in that one there is an op-amp and the inverting terminal. To the inverting terminal, you are from the input side you are connecting to a capacitor that is noted as C1, and feedback from the output to the input to the negative feedback is connecting to the inverting terminal through a resistance, feedback resistance RF. And for compensating the bias current, and here the we'll be connecting a resistor R Cont, which is same as RF. This is the circuit diagram of a basic differentiator, and the circuit performs the mathematical operation of differentiation. That is, output of this one V0 is the differential of this input Vi. Therefore, the output waveform is derivative of the input waveform Vi. That's called a differentiator. Let us analyze how can you get output voltage V0 as a derivative of the input Vi. Now this point N is the point. I am noting the end point, that is the inverting terminal point here. If you see that one, the potential of this N is same as, because of the virtual ground property, this is same as the potential of V plus. But if you consider this current is very small, this ground potential is same as this potential, so that the potential at this point terminal, that is Vn, you can say that Vn is equal to ground potential 0 volt. Another point is that if you consider an op-amp here, input impedance is very large, or that we take it as infinity, so that this current this current is also equal to 0. So these 2 points we have to consider before deriving this equation for this one. One point is that the voltage at this point is same as this point, or that's a ground voltage. Second is that input current Ia is equal to 0. But the node N is at virtual ground. That is, at virtual ground means this voltage is same as the ground potential, or Vn is equal to 0 voltage. And applying the Kirchhoff's current law at the node N, if you applying the KCL at this node N, the total input in the current coming towards the junction is equal to the current leaving from the junction. Therefore, here the current coming towards the junction equal to noted as IC plus feedback current IF, that is equal to II. IC plus IF equal to II. Since the input impedance, as I already explained, here the input impedance of the op-amp is very large, we will be taking as an infinity, so that the input current Ia is equal to 0. If the input impedance is very high or infinity, the current into the op-amp, that is Ia, is taken as 0. Thus, the equation 1 becomes, that is, if you see the equation 1, since this is equal to 0, we can say IC plus IF equal to 0. Now, let us see what is the current IC and what is the feedback current IF in terms of the voltages and the resistance as well as the capacitance. Now, if you see the current that is capacitor current IC is given by, it is the basic equation is IC equal to C into dVi by dt, or C dVi, that is whatever this the capacitor, that is C, you can write as a C1, it is noted as C1 into d by dt of the input voltage Vi minus the voltage at Vn, Vi minus Vn, d by dt of Vi minus Vn. But already we have seen Vn is equal to 0. That is why this input current IC is given by C1 into d by dt of Vi, dVi by dt. Therefore, that is the equation 3. That is a capacitor current. And the feedback current is given by, it is equal to V0 minus Vn divided by Rf. But Vn equals 0 means that V0 minus 0 divided by Rf, or that is simply it is equal to V0 divided by Rf. Therefore, feedback current equal to V0 by Rf, and capacitor current is equal to C1 into dVi by dt. Substituting this equation 3 and 4 in the equation 2 here, we'll be getting, substituting this one, IC equal to C1 into dVi by dt plus IF, which is equal to V0 divided by Rf, that's equal to 0. We are substituting equation 4 and 3 into equation 2, then you'll be getting an equation like this one. Or you can see from this one, it can be output voltage V0 equal to, if you take to the side, it is equal to minus Rf into C1 into dVi by dt. Therefore, output voltage is proportional to the derivative of the input voltage with a constant, that is the time constant, multiplication time constant, which is equal to my Rf into C1. But there's a negation is there because we are giving the input to the inverting terminal. That is why there's a minus is there. Therefore, the output voltage is given by minus Rf into C1 into dVi by dt is proportional to the derivative of the input. For output voltage V0 is proportional to dVi by dt. Thus, we can see that the output voltage V0 is a constant, that is minus Rf into C1 times the derivative of the input voltage Vi, and the minus sign indicates that there is a 180-degree phase shift of the output waveform V0 with respect to the input signal. Continuing the differentiator, this is the differentiator circuit as I already explained here, Rf, C1 and Rcop. And here the gain of the amplifier is given by output voltage divided by input voltage. That magnitude of gain is like that one. And if you take corresponding in S domain and converting S equal to j omega, then output voltage divided by input voltage is equal to magnitude of A equal to minus j omega Rf into C1. Or you can say that one gain is equal to omega Rf into C1. The gain of this differentiator is given by output voltage divided by input voltage, magnitude of the gain, that is given by omega into Rf into C1. Rf is a feedback resistance, C1 is the input resistance. Or you can say that omega equal to 2 pi f. Therefore, it is equal to 2 pi f into Rf into C1. That's a mod. Or you can say that one, this can be written as f divided by f0, where f0 is given by 1 by 2 pi Rf into C1. That is, if f0 defined as 1 by 2 pi Rf into C1. The gain is given by f divided by f0, where f0 equal to this one. And we can see that as the input frequency increases, the gain is increasing because it is proportional to the frequency. Therefore, at f equal to f0, you can say that at f equal to f0, gain equal to unity. The gain increases at a rate of 20 dB per decade. That is 20 decibel per decade. It is increasing the gain. Anyway, you understand that gain is increasing as the frequency is increasing. Therefore, at high frequency, the differentiation becomes, it will be unstable and produces oscillations. Therefore, at high frequency, it is unstable and that produces oscillation. That's the one problem with the differentiator. If a ideal differentiator, the problem is at high frequency, the system is not stable because as frequency increases, gain is going very high. Therefore, the system is become unstable. Another point is that at high frequency, again, we can see that the impedance is equal to, input impedance is given by 1 by omega into Ci. That is 1 by omega into Ci. C1 is the input impedance. Therefore, omega equal to 2 pi f. Therefore, at high frequency, again, you can see that one impedance is very large. Therefore, at impedance is very large. That is at input impedance, at impedance of the differentiator 1 by omega f decreases with the increasing frequency. As 1 by 2 pi f C1. Therefore, as f is increasing, the impedance is reducing. Therefore, input impedance reduces very much as the frequency increases, and then circuit will be that is sensitive to high frequency noise. Therefore, high frequency noise that will be sensitive. Therefore, these are the two disadvantages of this particular circuit. At high frequency, this is being because it is offering very low impedance at high frequency. Therefore, it is very noisy at high frequency is being affected by that one. Second is that at very high frequency system is not stable. Therefore, these are the two issues of a ideal differentiator. Now we are going to consider a practical differentiator. The difference is that there was no capacitor in the ideal differentiator, but we are adding a capacitance CF. This is additionally we are adding. Similarly, there was no input resistance CR1 in the ideal case, but we are adding R1. Therefore, this is the R1 and C1. Similarly, RF and CF. This is a practical differentiator because as we have seen in the ideal differentiator, there are two problems. One, at high frequency system is not stable and high frequency noise is also affecting. Therefore, the practical differentiator, this practical differentiator eliminates problem of the instability and high frequency noise. These are the problem for an ideal differentiator, that is instability as well as high frequency noise. These two things can be eliminated by introducing a capacitance across RF or at the feedback path. Similarly, an input resistance R1 in series to C1. Now, by this arrangement, the gain at high frequency is reduced, because in this case, gain is reduced significantly and thereby avoiding a high frequency noise and stability problem. These two problems can be eliminated by introducing a resistance R1 at the input side and a capacitance CF across the RF or in the feedback path. Therefore, this is a practical differentiator in which, for a good differentiation, thing is that this the time period of the input signal, that is the signal time period of the signal that is applied, that one, that should be much larger than or equal to this time constant, that is RF into CF. This time constant RF into CF is the but must be larger than or equal to RF into C1. It should be RF into C1, or here the time period should be much higher than RF into C1. That is, the time period of the signal should be much higher than the feedback resistance RF and the input capacitance C1. That is for example, here, if you consider a sinusoidal signal and that is given at the input side, output is given by, basically it is the derivative of the input. Derivative of the sine is equal to cosine. That is why this output is this one. This is the input and output is a cosine. It's a 90-degree shifted version of the input, and that is given by, this is the output, and the magnitude is decided by the constant, because the constant is the RF into C1. That constant, that magnitude will be deciding the magnitude of the output voltage. Therefore, this is if sinusoidal input is given at this, and you will be getting at the output is a cosine shifted version of this, 90-degree shifted version of this one. Similarly, if you give a square waveform, if it's a square waveform at the input, the output will be differentiation of this one. Differentiation of this one means, but of course there is a minus sign is there. It is equal to minus RF into C1 into dVi by dt. That is why here if you differentiate this one, if it's a positive side, suddenly if it is dVi by dt, because it is changing from 0 to this certain value 1 volt suddenly, with that is why dVi by dt will be very large. That is why we will be getting spikes. Therefore, but there is, since there is a negative sign, minus RF into C1, you will be getting a negative spikes. Therefore, during the positive rise here, you will be getting a negative spikes. Similarly, for a negative plus 1 to minus 1, it is shifting from here. That is why you are getting a positive, because minus RF into C1 is, that's why you are getting a positive spikes. Therefore, when there is a change is happening, only you will be getting a spikes. But when it is a constant, when there is no dVi by dt is not there, if you are taking a constant voltage, dVi by dt equals 0, that is why you are not getting any voltage. But whenever the voltage is changing from some value to another value, in this case it is changing from minus 1 volt to plus 1 volt, then you will be getting a spikes in the negative side, here a positive side, negative side, like that one. Therefore, this is the input to this differentiator, and output, derivative output of this one with a op amp is minus RF into C1 into dVi by dt, that is a spikes. Last slides we have seen the working of an ideal differentiator and the issues behind an ideal differentiator, and then what is the practical differentiator. Like that one, integrator, let us see integrator. When you consider the integrator, the position of capacitance and resistors, they are interchanged compared to the differentiator. Therefore, previously in differentiator, input capacitance was the input side and resistance was the feedback. But in integrator, the capacitor will be the feedback path, that is between output and this inverting terminal, and the resistance will be at the input side. Therefore, this is the ideal integrator in which output voltage is the integration of the input voltage, V0 equal to minus 1 by R1 into CF into integral Vi dt. Therefore, that is the ideal integrator, and this is the compensating resistance, which is same as the Ri. Therefore, here in order to analyze this equation here, as we already explained in the last case, here this is a virtual ground because this potential equal to 0, voltage at this point is equal to 0. Another point is that this input current is also 0 because it's having an infinite input impedance. Therefore, this input current to the op-amp equal to 0. And this is a feedback current. What is the current flowing from the output to this? This is a feedback current, and input current is from input point Vi into the N. That is the input current. Now, writing the nodal equation, if you apply the nodal equation at this point here, that is current coming towards the junction is equal to current leaving from the junction. That is assuming that input current of op-amp is equal to 0. That is, since input impedance is very large, infinity, this current, input current is equal to 0. Now applying the nodal equation at this point, what is the current coming towards this one? Vi minus Vn divided by R1. Vi minus Vn divided by R1. Then plus feedback current is given by, it is equal to C dV by dt, or it is equal to Cf into d by dt of V0 minus Vn, V0 minus d by dt of V0 minus Vn. That is this current. That is equal to the input current, but input current equal to 0. That is why that is equal to 0. Now expanding this one, another point is that the voltage at this point Vn equal to 0. That is why substituting that one, Vn equal to 0, we will be getting it is equal to Vi divided by R1 plus Cf into dV0 by dt, that is equal to 0. Therefore, that is the equation 1. And here, if you rearrange this one, we'll be getting the dV0 by dt, or output voltage differentiation with respect to time. dV0 by dt is equal to, it is equal to, what is that? It is equal to minus Vi divided by R1 into Cf. Or integrating both sides here, dvi, and integrating both sides, we'll be getting integral 0 to t dV0, integral 0 to t dV0 equal to minus 1 by R1 into Cf integral 0 to t Vi dt. Or this is equal to nothing but output voltage V0t. That is, output voltage is equal to minus 1 by R1 into Cf integral 0 to t Vi dt plus the initial voltage, output voltage, that is equal to V00. This is the initial output voltage. Then, therefore, this is the output equation of this integrator, which is equal to minus 1 by R1 into Cf integral Vi dt plus the initial value of this voltage, because this is an integrator, previous voltage is also will be getting added. Therefore, this is the equation for the integrator, and the output voltage is proportional to the time integral of the input. That is, it is equal to my R1 Cf is called the time constant of the integrator. Therefore, there is a negative sign. That negative sign means that output voltage is an inverted version of the integral of input. Therefore, output voltage, and therefore this integrator is also known, it's called an inverting integrator. Since the output is here, there's a negative sign is there, this is called an inverting integrator. Therefore, a resistance R-comp is connected, which is equal to the input resistance R1 is usually connected at the input terminal to minimize the effect of input bias current. To reduce the bias current, we are connecting a compensation resistance. Now, this is a ideal integrator. Now, let us see what are the issues of this ideal integrator. And of course, there is a practical integrator that will be coming later. Now, what are the issues? One thing is that if you if you bring this capacitor at the input side using the Miller theorem, which I already explained the previous presentation, if you bring the Cf at the input side, that will be reflected as 1 minus AV times Cf, 1 minus AV times Cf. But gain of this amplifier is very, very large. AV will be very large, so that 1 minus Cf AV, that will be very large, where AV is the open loop gain, which will be very large, it will be infinity ideally. So the effective, meaning that this capacitance that is be reflected here will be very large, or the effective time constant, which is a product of capacity, effective time constant is equal to whatever the product of this resistance R1 into this capacitance Cf into 1 minus AV. That time constant will be very large. So the effective time constant of op-amp of the integration becomes and will be very large, and resulting in imperfect integration. Therefore, in a practical case, we cannot use because of the high value of the capacitance reflected at this one, the time constant will be very large. That's the one issue of the ideal integrator. Continuing the integrator, that is ideal integrator, it is simply R and C. R the input side, it can consider like as a C is a capacitor between output and input, like with RC also. This is working as an integrator, something like that one. In that the voltage ratio, output voltage is divided by input voltage, that's equal to, if you take it in a S domain, V0 is equal to VIS into minus 1 by S into R1 into CF. This is a transfer function. If you take V0S divided by VIS, which is equal to minus 1 by J omega R1 to CF. Or if you take the magnitude of this transfer function, that's the gain. This is called the gain, output voltage divided by input voltage, and that is equal to 1 by omega R1 into CF. Or here, if you see omega, it is equal to 2 pi f R1 into CF. Omega means it is equal to 2 pi f R1 into CF. And the gain in dB, if you calculate, it is equal to 20 log V0S divided by VIS. Therefore, the integral gain can becomes in 0 dB. When A equal to 1, the gain will become, when this is equal to unity, we will be getting the gain equal to unity. Therefore, at omega equals 0, the magnitude of integrator transfer function becomes infinity. And we can see that 1 by omega R1 into CF, 1 by omega R1 CF is the magnitude of this gain. Gain magnitude is given by 1 by omega R1 CF. Gain magnitude means the magnitude of output voltage divided by magnitude of input voltage. That is given by the gain of the integrator. That is given by 1 by omega R1 into CF. Omega equal to 2 pi f. Or it is equal to, if you see that 1 by omega R1, if it is equal to unity, that is, if V0 is equal to Vs equal to unity, then we can say that omega R1 CF equal to unity. Or here, if you see that one, omega equal to 2 pi f naught, which is equal to 1 pi R1 CF. Or we can say that one, thus, it is FB, it is written as FB. 2 pi FB equal to 1 by R1 into CF. Or FB is given by 1 by 2 pi R1 into CF. Or the gain of this this one, integrator, the gain of the integrator is given by 1 by omega R1 into CF, and we can see that one omega equal to 2 pi f. Therefore, as frequency is increasing, the gain is getting reduced. Therefore, one problem, that is the one observation we can get from this one. Another point is that if at all there is a DC voltage at the input side, at a DC voltage, then the feedback capacitor gets open circuited, because for a DC voltage the reactance will be infinite, or the feedback capacitor behaves as an open circuit, and there is no feedback for the DC signal, and the op-amp thus operates as an open loop, resulting infinite gain. Therefore, the input side, if there is a DC voltage, that will be acting as that will be producing, the capacitance get open circuited, or output will be very large, or that will be driving the op-amp into saturation. Therefore, in practice, the output of op-amp never goes to infinity. It cannot go to never. That will be saturating either to plus VCC or minus VCC. Therefore, in ideal case, if you consider an ideal case, if there is a voltage, DC voltage at the input side, that will be integrated, and that will be due to the capacitance value, since it is open circuited, that op-amp will be go into the saturation, and that working of op-amp gets it will be affected. Therefore, that is one issue, that if a DC voltage at the input side will be making to bring the op-amp into saturation. For the continuing the integrator, the DC voltage at the input of op-amp integrator leads to saturation of op-amp output to either plus VCC or minus, or plus VSAT or minus VSAT, depending upon the DC voltage polarity. Therefore, that is the problem. If it is a DC input at this point is there, this is getting saturated. That is, as the gain of the integrator decreases with increasing frequency, because it is 1 by omega it is 1 by omega frequency, it is inversely proportional to frequency. Gain is inversely proportional to frequency. Therefore, as frequency increases, gain is getting reduced. The integrated circuit, integrator circuit does not have a frequency problem like a differentiator. For at high frequency, there is no problem like a differentiator, because as frequency increases, gain is getting reduced. There is no problem of instability in the case of a differentiator, in the case of integrator, unlike differentiator. However, at low frequency, the problem is that At low frequency, because of the DC voltage coming at this one, the gain becomes infinity and op-amp is getting saturated. Now, the problem with the integrator is that not at high frequency, at low frequency or near to the DC voltage, if there's a DC voltage at the input side, this op-amp gets saturated. Now coming to the practical integrator circuit, that's also called Lossy integrator. In this case, apart from the feedback capacitor, there's a resistance RF is added at the feedback path, and the gain of that integrator at low frequency at DC can be limited in order to avoid the saturation of op-amp if the feedback capacitor is shunted by a resistor RF. We are shunting a resistance RF so that the going saturation for a DC input voltage that is avoided by introducing a resistance in the feedback path. RF is introduced. Then parallel combination of CF and RF behaves like a practical capacitor. This behaves like a practical capacitor. That is why this is sometimes called as a Lossy integrator. Another name is called Lossy. This is a practical capacitor in which there's a capacitance, ideal capacitor in parallel with a resistor. Therefore, this is can be considered as a Lossy integrator. Therefore, the resistance, feedback resistance RF limits the low frequency gain into RF divided by RF. For when a DC voltage coming here, it won't go into saturation, but that is limited by this ratio RF divided by R1. Therefore, the resistor RF limits the low frequency gain to minus RF divided by R1 and thus provides a DC stabilization. That is the idea of providing a resistance across the capacitance. If the input frequency is lower than in lower frequency, this frequency which is equal to 1 by 2 pi RF into CF, 1 by 2 pi RF into CF, FA, that is defined as FA. This is a lower frequency of integration. Lower frequency of integration is given by 1 by 2 pi RF into CF. Now, meaning that if the input frequency is lower than this frequency, 1 by 2 pi RF into CF, this circuit acts like a simple inverting amplifier. It is working as an inverting amplifier provided the input frequency is less than 1 by 2 pi RF into CF. To get an integration, it should be the input frequency should be more than this one. For perfect integration, to get a better accuracy, the input signal should have, the thumb rule is that 10 times this limit. Therefore, 10 times this frequency should be 10 times FA. If the input frequency is 10 times this frequency, 1 by 2 pi RF into CF, there will be perfect integration can be obtained. Therefore, this is a practical integrator in which only difference is that you are adding a resistance RF across the capacitance CF. Previously, we have seen a inverting integrator in which the input is given to the inverting input. Rather than in this case, the input is given to the non-inverting input. Only thing is that resistance capacitance. Again, there is a resistance capacitance feedback. This is a circuit diagram for a non-inverting integrator. Same way you can apply this theorem like you can find out what is the ratio of output voltage to the input voltage. And in this case, first you will be finding out what is the voltage, which is equal to what is the voltage at this point, that is what is the voltage coming at this point you are calculating, what is the voltage at this point, which is equal to this, what is the voltage is 1 by SC divided by 1 R plus 1 by SC into the input voltage. That is in S domain it is taken. And similarly, once you get this voltage, output voltage is behaving as a non-inverting amplifier, that into whatever this one, that into of course 1 plus this feedback capacitor 1 plus RF by R. Okay. RF means the capacity, because here the impedance is the 1 by SCS divided by R into V dash. Or you can say that if you reduce this one, you can get it that the output voltage is given by 1 by R into C into VI. R into that input resistance and the feedback capacitance C here, that into VI dt. There is no inversion, and there is no negative sign. Only the equation is same. Output is the integral of the input on 1 by RC. That is also, there is no difference. But there is no negative sign. That is why it is called a non-inverting integrator. Therefore, there is no phase inversion between the output and input. That is why this is called a non-inverting integrator. But we are concentrating only the inverting integrator more. Coming to a problem, this is a basic in integrator. The feedback path, there's a capacitor. Input side, there's a resistance of 100 kilo. This is a 10 microfarad capacitance is there. Question is that if an input of this square wave is given, what will be the output? Is an integrator. What will be the waveform at the output side? Now output is, of course, it is an integral of the input, which is given by, which is equal to minus 1 by R1 into CF integral Vi dt, minus 1 by, in this case it is R, it is written as R, for minus 1 by RC into integral Vi dt is the output voltage. This is a basic equation. And here the R and C is given. R is equal to 100 kilo ohm, C equal to 10 microfarad. Substituting that one, the time constant will be getting, it is equal to 1 second. And substituting this one here, output voltage is equal to minus integral Vi dt. Therefore, this is the equation for the output voltage in terms of the input voltage Vi dt, it minus of integral Vi dt. Now, let us see this one from 0 to 1. From 0 to 1, what is happening? From 0 to 1, if you see that one, if you integrate this one, integral Vi dt, here it is a straight line. Therefore, if you integrate a constant value, if you integrate a constant value of 1, integral 1 dt, if you take integral 1 dt, it is equal to t. Integral 1 dt means it is equal to t, or it's a straight line equation, but there's a negative sign is there. That is why during this 0 to 1, it is a straight line equation, and in that one value is equal to, it is saturating to minus 1, because there's a minus sign is there. Similarly, from 1 to 2, again here it is a positive voltage, it is equal to minus 1 volt for this much time. Therefore, again if you see integrating that one, integrating a constant, that will be a straight line equation. From this one, again if you with a positive slope, because already there's a minus there, a minus here, that will become positive. From this one, you'll getting a positive slope that will be reaching at this 0.2 here, which is equal to there it is equal to 0. Then this is the output waveform corresponding to a square input here. The output is like this one. You will be getting a, it's a triangle only. It's a triangle with a negative sign is there. That is why it is getting at the downward portion of this axis, because there's a minus sign is there, minus Vi dt. Therefore, this is the input waveform of an integrator, and this is the output waveform. Since we are getting a constant voltage during this period, it will be a straight line equation, and if the minus time comes, it will be a positive slope, negative slope, like that one. This is a practical integrator in which the feedback capacitance and resistance they are given. Question is that what is the lower limit of the input signal frequency? That's called the critical frequency. That is given by, as we have already seen, it is equal to 1 by 2 pi this resistance RF into CF, or 1 by 2 pi RF into CF means 1 by 2 pi into 100 kilo ohm into this 0.01 microfarad, or that will be getting, you will be getting, it is equal to 159. That's therefore, if the always the signal should be, the input signal should be more than 150 hertz. If it is less than, there's no integration, it is simply working as a inverter. It will be working as an inverter. That's the meaning. That's called the critical frequency, below which it won't work as an integrator, which is equal to 1 by 2 pi RF into CF, which is equal to 150 hertz. This is another problem relating to the differentiator. Differentiator means, as you know that one, the capacitor will be at the input side and feedback is the resistance, and that is given by C C1 into RF into dVi by dt. So it is, in this case, it is equal to R into C into dVi by dt. Of course, there's a, since we are applying to the negative input of the op amp, it is equal to minus. Therefore, output voltage is the derivative of the input, minus RC into dVi by dt. That is the basic differentiator. Therefore, if you differentiate a square waveform, what will be that one? In this case, problem is that find out the output voltage if the input is changing from 0 to 5 volt in 0.1 millisecond. That is, from 0 to 5 volt, if you magnify this one, it is not suddenly, the change is taking place for a time of 0.1 millisecond. From 0 to 5 to change, it takes 0.1 milliseconds. Then you can calculate what is the rate of change of voltage, dVi by dt. For 0 to 5 is the change, and that is taking place 0.1 millisecond. Then you can calculate 5 divided by 0.1 milliseconds, or 50 volt divided by milliseconds, or 50 into 10 raised to 50 volt into milliseconds, or 50 into 10 raised to 3 volts per second. That is, this much is the dVi by dt. Then RC you can calculate. What is the product of this R and 1 kilo ohm and 0.1 microfarad? That is also you got. You got RC and you also got dVi by dt. Then you can calculate what is the output voltage, which is equal to the product of this one, RC into dVi by dt. And then you will be getting it is equal to minus 5 volt. It is that is as it changes here from 0 to 5 volt from 0.1 seconds. Here you will be getting a voltage spikes of minus 5 volt. Again, if you come to here, if you again at this point again the voltage is changing from plus 5 to 0, plus 5 to 0. That is why then at this point you will be getting, if you again calculate, you will be getting plus 5. It will be same way, you will be getting plus 5 spike. The spikes is equal to plus 5. Therefore, when it is changing from 0 to positive 5, it will be getting a minus, because there's a minus sign is there. Therefore, minus 5 volt. When it is changing from plus 5 to 0, again the change is equal to 5 volt, but the polarity equal to plus 5. Therefore, this is equal to plus 5. Therefore, when a waveform of this type is given at the input of a differentiator, output will be a series of spikes getting the amplitude is decided by this one minus RC into dVi by dt, and the polarity, of course, it is the minus sign shows that whenever there is a positive change plus 0 to 5 volt, you will be getting a negative spikes, and when this change from plus 5 to 0, you will be getting a positive spikes. For an input of this one, you will be getting output output of like this one for this differentiator. The first signal quickly returns to the 0 as the input signal. Because it is returning back. Why it is returning back means this is dVi by dt equals 0 after this one, because when a voltage is constant, dVi by dt equal to 0. Then that is why it is suddenly returning back to this one. This is appearing as a spikes because dVi by dt equal to 0.